So, good afternoon. Today I will be going with the topic stochastic process. This topic required in 5th semester of BSc Statistics. So, today I will be teaching you stochastic process. So, what is basically stochastic process is, it is a mathematical model which depends on random variables or probabilistic models, which those models and variables depends on time and state space. If we see on the definition, what it's come that stochastic processes are mathematical models used to describe random variable or probabilistic phenomena that evolve over time or space. That means probabilistic phenomena that evolve over time. It's depend on time. Something is happening in case of time. So we will say in probabilistic phenomena, in probabilistic way. So families of random variable which are functions of say time are known as stochastic process. Families of random variables means if we have random variables say x1, x2. In statistics, random variables is said as okay x1, x2, x is a random variable which can take any variables at a particular time or particular space. So those random variables say like this. If we say random variables, families in the sense like this, okay, x1, x2, x3, x4, like this way up to if you take to n. Okay, so we can say n is greater than equal to 1. Obviously, n should be greater than equal to 1. Okay, so say these are the, if we give it the name as p, so these will be the families of random variable. Okay. Yeah. So, which are function of say time are known as stochastic process, okay, or random process or random functions. So they are often used in various fields such as finance, engineering, physics, and many more. So let me go with examples. Here, see, suppose that xn is the outcome of n toss of a coin. So here n is greater than equal to 1. That means we have coin. If we take a coin, we have two phases, okay, head or tail. If we toss the coin, then we will get outcomes either head or tail. So xn is the outcome of nth toss. We have 1, 2, 3 up to nth toss. Okay. So xn is, if we take here x1, so it will be the first toss, x2 second toss, third toss. Similarly nth toss, okay, of a coin. And yeah, mention it like coin should be unbiased. Okay, then this sequence of x and n which is greater than 1 is a family of random variables such that for a distinct value of n, which is 1, 2, 3 up to infinite, we can toss many times as we want. So one gets a distinct random variable x and n which is greater than equal to 1 constitute a stochastic process known as Bernoulli process. Now here, what is Bernoulli process? Actually, Bernoulli process take two values at a time. Okay. So if we get, say we want head. Okay, at a time we want head. We need the random variable of head. How many times the head has been occurred? So we will define head as say 0. Okay, or sorry, or 1. And tail we don't need tail, so the we will decide as okay tail as 0. So how many time has been the head occurred? So the process will be either 0. First, say first toss has occurred as head, so we got 1. Second toss tail, we will say 0. Similarly head, again third toss will be head, fourth toss head, fifth is like this. So we have okay two outcomes, either 0 or 1, that means head or tail. That's why we say as Bernoulli process. Okay. Number 2 we have taken here, suppose that xn is the number of sixes in the first nth row. Okay. Xn we have taken number of sixes in first nth row. In first nth row in sixes, where does it come? Here I have taken of die of a die. Okay. So we have a die, we have 6 phases. Okay, we have thrown die, so we will get different values in different set of time. So we have calculated only 6, outcome of 6. Okay, so in the first and throw, say we have thrown the die 10 times, so we got 4 sixes. So that xn, there will be x4. Okay, that we have 4 sixes. Okay, in first and throw. Now for a distinct value of n, say 1 to up to infinity, we get a distinct binomial xn where n is greater than, which gives a family of random variables, is a stochastic process. It's a binomial variable because we have sixes. We want a single process, 6. How many times? 10 times, 11 times, 4 times, as many as we want. Okay, in first and through. Okay, so it will constitute binomial distribution. Now let us see type of processes. What are type of stochastic processes? Okay, so there are 4 type of stochastic processes. Number 1 comes discrete time and discrete state space. Okay, so what is state space actually? Discrete time is, we could say, the time we measure time in a 1 hour, 2 hour time in a specific way. Okay, some specific regarding some criteria. So state space is number of outcomes or number of some processes. Okay, number, it's a qualitative. See here, examples are number of sixes appearing in first and throw of a die. Here time is, okay, number of sixes appearing throw and throw. We are throwing die, it's discrete. Okay, we have one time, first time, second time, we have thrown like this. These are discrete. And number of sixes is countable. We can count. The sixes are countable, so it will appear as discrete state space in discrete time. Okay, then come discrete time continuous state space. Here example, number of road accidents per day. Okay, time is per day. We can calculate day to day, 24 hours. Again next day, we can say in a month there are 30 days, so we can calculate accidents per day. First day, okay, this we can count it as discretely. And continuous state space is number of accidents. So accidents are, it can be continuous. Today we had 4 accidents, tomorrow we will have, maybe, we don't know, but from the first of the month we can have, okay, accidents, say like in the first month we had 3 accidents, then 2, then 4, like this. This will be continuous sense. Okay, so then third is continuous time, discrete state space. Time should be continuous and state space that should be discrete. Here number of incoming calls at a switchboard in an interval. See, here it is an interval, we given as an interval 0 to t. So it's a time based. Okay, that means continuous time. Say t, if we take t as say 4 hours or 10 hours. Okay, so in 0 to 10 hours, means in between 10 hours, how many incoming calls has been came in the switchboard? So that's countable. Incoming calls are countable. Okay, but time we have taken continuous. Then in fourth, continuous time and continuous state space. Okay, so here xt represent the maximum temperature particular place. Here also time has taken 0 to t. Okay, in a bounded series. And the maximum temperature is counted as a in scale. It's not quantitative, it's qualitative. We are feeling hot, 33 degree, 34 degree, like this. So it's come on continuous time. Okay, next, the most important is the Markov process. Okay, here see what given. Markov process here, if xt, t belongs to capital T, t represents here time. Okay, is a stochastic process such that given the value xs, the value of xt, okay, that is t should be greater than s, do not depend on the value of xu. Okay, xu where u is less than, should be less than s, then the process is said to be Markov process. See here I have written in mathematical way that u should be less than s, u should be less than s, and s should be less than t. Okay, say u, s and t are the given like x and t. X is random variable, depends on time. Say s is a time. Okay, so they are depend on time. So if u is the occurrence of now some outcome, So it should be less than the next occurrence. Again, it should be less than the future occurrence. Okay, this what says actually. So if we take the random variable here, x of u, x of s, x of t, so it will come like this. Okay. So for 1, 2, 3, these are the, say, t is the final time. Okay, t is the final time, and t1 are the sub time. Say we have given final time of 10 hours. These are, say, 1 hours, 2 hours. Obviously 1 hour will be less than 2 hours, 2 hours will be less than 3 hours in this case. Okay, so if we take now probability of a, say some occurrence, some situation less than xt, again it's less than and equal to b is another some bounded v, some occurrence. Okay, xt should be in between a and b, some given that x of t1 equal to, say, x1, x of t2 like this up to xn will be equal to probability of a, which is less than equal to the whatever it is. So given that xn, which is equal to 2, that means it says that stochastic process or Markov process, if whatever is happening now, it's totally depend on recent past. Okay, so what are the recent past? See, xt has already been occurred, then only x2 will occur, then only after that xn will occur, like here x t1 t2, after then t has been occurred. So this will depend only on xn, because after this what in probability says, okay, after this what it says, that probability of a less than equal to x t is less than equal to b, given that all these things. Okay, so this will depend on the very last occurrence. The process xt, t belongs to t, is a Markov process. This process is called the Markov process. Okay, so what is Markov chain? Now what is Markov chain? It's simply defined as the dependency that the outcome of n plus 1th trial depends directly on that of nth trial and only on it. Okay, so chain itself says it should be connect to each others. So here it's simply dependency defined as dependency of outcome of n plus 1. Means that means n we have occurrence like from 1 to up to nth occurrence. So to get the n plus 1th trial, we need to know about nth trial. That means nth trial should occur first. Then only you can get the n plus of 1th trial. After, before n trial, there has many trial has been occurred. But Markov chain says that only depends on the very past trial. Okay, that is present, the very past trial. Say if we take the probability of Sn is the sum of n numbers. So n plus of 1, it will say like nth sum of nth has been occurred, sum of nth numbers has been occurred. This is the after n. So it will be, say, j plus of 1, given that Sn, which is equal to j. Obviously j has occurred and only j plus will be occurred. So we have taken it as p. If we say it's probability, that means if Sn plus of 1 occurs j plus of 1, then the probability will be p, and if Sn plus of 1 occurs j, then the probability will be q. Okay, the concept of saying this all depends on the very past occurrence. Okay, now the example of Markov chain is, one of the example is Poisson model. So here there is a example here. An urn contains, say, B black ball and R red balls. Okay, we have B black balls and R red balls. A ball is drawn at random and is replaced after the drawing. Okay, ball has been drawn at random and is replaced after drawing. After drawing, we have replaced the ball. So whatever the ball, red or black, then that is drawing is with replacement. That means whatever we will draw, the drawing ball should be again replaced in the urn. Okay, the outcome at the nth draw is either black or ball, whatever it will be, black or ball. We don't know, because probability is always, we don't know what the future occurrence is. We always take something out, and that outcome is what probability we decide total out of total. So let the random variable xn be defined as this one. If we will take when black ball occurs 0, when sorry, I have done mistakes here. Okay, one, when black balls will occur, so 0 will be red balls. So there are two possible outcomes, b by b plus of r and r by b plus of r. How it will occur? As we have said, 1 will occur. So when xn equal to 1, that means black balls, and when xn equal to 0, that means red balls. We have occurred black balls. We have drawn a ball. It has occurred as black. So the what probability says what we have in hand, total what have we have b plus of r balls. So the total comes here, and what occurs, what the outcome is, we put in the numerator. Okay, so this is how probability occurs, b by b plus of r. Similarly, in the second draw, we got, okay, 0. The probability of occurring of r, that is 0, is r by b plus of r. Okay, now we have, see here, since we have probability of x2 which is equal to 1. Okay, the probability of x2, the second draw, which is 1 is what, our black ball. So here what we will do, here it's come, there is a condition that the past should occur, the we should know the past occurrence. Okay, this is the present occurrence, that the second trial you have got black ball. So what will be the past occurrence? We don't know what will be past occurrence. It may be black, it may be red. So we have taken it may be black or it may be red. Okay, so this is the formula. You already know what is the formula of probability. This probability of A given of B is equal to what? Probability of A intersection of B divided by probability of B. So if we take this over here in left hand side, A given of B into probability of B equal to probability of A intersection of B. Okay, this we know already, we have gone through in our first semester. So these are formulas we put in this formula. So here see, b plus c, how it came, b plus c, the first occurrence here, yeah, here the first occurrence is 1, that means your black ball. So what we have said here, conditions is that when we get a black ball, we have to replace, also we have to add some of the c balls. Spoilers and model says that when we get a black ball, we will replace, also we will add some c balls. Okay, we are not adding amounts, or we are not talking about amounts, we are saying we are adding c number of balls. Quantity is not here, we have quality. So there will be C balls will be added, and the present ball is, okay, C black ball. So it will be B plus of C. We have total B plus of R plus of C. Okay, because we have already got, okay, black balls, so we have to add C. So the present is we got black balls, so we got black plus we already have C balls. So yeah, total will be B plus of R and plus of C, and here black getting of black ball is B plus of R plus. Here we got what? 0. We got 0. That means we got red ball. So we got red ball over here. So in total, what will have B plus of R? But in present outcome, we got black ball. So what happens, there is a condition when we get in present, when we get in past occurrence, that is red ball, but we get in the present occurrence, that is the black ball. What we do, we replace, we add some of the C balls in the urn. C balls in the urn. So here that's what the probability comes, B by B plus of R plus of C, because here we got the black ball, so we have added here. This is the conditions. Okay. So for 0, it will be obviously R by. So after calculating, we got this. Okay. So also, in this line, so again, if we take the third occurrence, the second occurrence has been given 1 1. So obviously we need first occurrence. So what will be first occurrence? Either 0 or 1. So we have to calculate the similar way. Here you can see that we get 0, that means red ball, and 1 1 we got black ball. So we got black ball. So we have added C number of black balls. C number of some balls, and again we got in the present occurrence what the black balls. So we have again put C number of balls in the urn. So that's why our already we had okay B plus of R plus of C, because in the past occurrence what we had black balls, so we have to add C number of balls. So B plus of C we had, and after we I have told the conditions that when there will be black red balls, so if the occurrence in the present occurrence it comes the black ball, so we have to add again C number of balls. Okay, so similarly you can understand the thing, same things we have done, just the thing is you have to see if 0 has been occurred in the first trial. So the in the present trial, if one is has been occurred, that means the black ball has been occurred. We have to add another C ball. Okay, sorry. So like this, you have to calculate this. After calculating, we got the probability this, which is the Poisson model. Okay, they are okay. So there are some conditions actually. See, if we take here the formula is already formula, probability of A given of B is probability of intersection of B by probability of B. The if we calculate this, we will get B plus of C and B plus R plus of C. Okay, but in the process, if we go in the process, so what will be the process here? Given what x3, the third trial is 1, second trial is 1. So obviously we need the first trial. We have taken first trial. After taking first trial, we got these values, we got different values. After adding these, we got different values. So it becomes different. So here it becomes different. So what does it says? That here the condition of probability x3 given x2 is not equal to that x3 given of x3 and x1. Because here only we have taken x3 and x2. We have excluded x1. We have excluded x1. So obviously there will be the process, the left hand side or right hand side will not be equal to those, because the value will be missing over here. So therefore the Markovian property is not satisfied, and the stochastic process, this is the stochastic process defined for Poisson model, is not a Markov chain. So let's finish this chapter up to here. We have many other details. We will talk after for the next class. Thank you.